Welcome to Chemistry 111. Yesterday we had finished reviewing for the test. The test has been sent out. The test is due Sunday. Just a quick reminder, it's in two parts. The first part one, is 9 questions. All of them include file uploads. So what does that mean? It means I'm going to give you an hour and a half to do 9 questions, which is about 10 minutes a question because of the added difficulty of doing that. The idea being, when you'll have a thing like draw a Lewis structure, A of H2O. So you'll either on a piece of paper or on a whiteboard, whatever, to do that, you include all your valence electrons. You'll then take a picture. Next step, this is what you might want to do some preparation. The best, easiest thing to do would be if you have Google Drive on your phone. You could then just upload to Google Drive. And then last step is then attach the file in the test via Google Drive. Otherwise, you might have something like you might need to email it to yourself, or you might need to have some SIM card or some way to transfer the data onto your computer. Easiest way would be upload it to a file sharing cloud, upload it to the cloud, and then quickly attach it. But there's 10 minutes a question because I expect that's going to be a major hassle. So that's the best thing I can do considering what we're doing. If an hour and a half doesn't seem like enough time, we'll sort this out and let me know. Still couldn't get them all done. Whoever tries it first or tries it second or third and struggling with the time limit, let me know. There's also going to be net ionic equations. You'll get some silver. Write the net ionic equation for this combination: silver nitrate, aqueous, and say sodium chloride, aqueous. Write the thing for that equation. So step 1, which is going to be all the step 1 for all of them, use double displacement. So you'll have sodium nitrate is the byproduct, and silver chloride. Sorry, you don't know this is aqueous yet. Step 2, cross-reference the compounds onto the solubility chart. You see sodium nitrate, oh, that's aqueous. Silver chloride, well, that's a solid. That's going to be precipitation. Step 3, break up the ions. Anything that is aqueous can break up into the cation-anion pair. Everything that is solid or liquid, here's a hint, the only liquid we'll have is H2O. Solid or liquid do not break apart. So we do not have to worry about those. Then finally, everything that is aqueous and ionic and same on both sides of the arrow. So in this case, sodium nitrate becomes spectator ions and cancel out. So the answer for this one would have been, what is the net ionic equation? You'd say silver plus aqueous, chloride minus aqueous, goes to silver chloride solid. So you'd take a picture of that, you would upload that to your file. But I'm just showing you an example of there's going to be 4 questions like that, 4 questions like this, whether it's acid base or net ionic equation, or acid base or precipitation, the same general thing. You write a net ionic equation for that. So that is a quick rundown on part 1 of the test. Part 2, you have 2 hours to finish the remaining, like 16 questions, something like that. Almost all multiple choice or drag or drop down or check mark. So there's that. No, I don't believe there's any homework due this weekend because we got ahead of where I was expecting to be in the notes. So we'll still have the test this weekend, but the actual homework for this test is not due till next week. However, I do try to base some of the test on the homework. So at least giving some of the homework an attempt probably wouldn't be a bad idea. Yeah. But let's go ahead and start in with the notes. So we're moving into the next chapter. I'm not sure how far we'll get. I have an idea where we're going to stop because this is where we start to get into the math. This is where if you're struggling with math and you know you're struggling with math, find some time to come see me. Come bug me in lab. I know I may get a little frustrated with some people sometimes, but I do desire to see you all and help you if you need help. Just a little stressful with chemistry week starting next week. But come get help if you're struggling with dimensional analysis, because dimensional analysis is where we're going. Yes, you could memorize a bunch of equations, but it becomes a lot of stuff that is very specific. But if you learn the steps and you learn your dimensional analysis, you can get by. So we're starting our math. Stoichiometry. So, oh, for God's sake. Okay, there we go. It should be loading. Basically, last chapter, we learned how to balance a chemical equation, but not necessarily why do we need to do it. And the idea of balancing a chemical equation, besides just giving you a nice, tidy little thing, is that we can use the stoichiometry as a guide to how these guys should be mixed together. Stoichiometry is the calculation of the amounts of substance within a reaction. The purpose of the balanced equation is that coefficients will tell us the ratio at which molecules will react. Saying that if I know how many molecules of potassium chloride I formed, I can figure out how many molecules of oxygen I should also form. If I know how much potassium chlorate I have, I know how much potassium chloride I can generate. So there's ways to use this equation. This says 2 potassium chlorates decompose. When they decompose, it produces 2 potassium chlorides and 3 oxygens. We can look at this on a molecular level of just 2 molecules, 2 molecules, 3 molecules, but we can also scale it up at any ratio. We can do 2 moles. Remember, a mole is 6.02 times 10 to the 23rd atoms or molecules or whatever. So we can have a double butt ton of potassium chlorate produces a double butt ton of oxygen. We're just simply saying we have a ratio of 2 to 2 to 3 whenever this reaction goes through, based on this balanced chemical equation right there. Scaling this up, if I want to do a huge reaction, 30 moles of potassium chloride would produce 30 moles of potassium chloride and 45 moles of oxygen. It's here. So we are going to be able to use this to scale up from any scale. The first thing we're going to need to do is we're going to need our dimensional analysis, how we're going to use this. Now, when beforehand, you could get by with semi-simple conversions. But what we got to do now is we got to learn the dimensional analysis kind of railroad track method. Here's a quick little refresher. If we wanted to convert, say, we have 75 centimeters and we wanted to know how many kilometers that is. We want to go to kilometers. How we would do it, railroad track dimensional analysis method, is I would figure out the conversion of centimeters to meters and meters to kilometers. So I'd start with 75 centimeters over 1. Then I would say, well, there's 100 centimeters in 1 meter. So I'm going to set this up. So I'm multiplying by 1 meter divided by 100 centimeters. Why I'm doing that is so that centimeters is on top of the bar and there's a centimeters on bottom of the bar. That eliminates my previous unit and leaves us with meters as my unit. Then I would know that there is 1,000 meters in 1 kilometer. I know I need to divide by 1,000 because I currently have a meter on top. So I need to match it with a meter on bottom. We had centimeters, so we divide by 100, then we'd divide by 1,000, and that would give us how many kilometers 75 centimeters are. It's a really small number. It's a silly equation. It's a silly number. But you got to remember, we also learned how to do moles. How do we turn grams into moles, moles into grams, grams into atoms? We did the same thing. There's an equation. You don't have to memorize the equation if you understand molar mass. If I have 31 grams of carbon, and I want to know how many moles of carbon, I would look up the molar mass of carbon. And I would use that. So 31 grams, there's an equation. I don't even bother memorizing the equations because dimensional analysis. I look up carbon is 12. So I'd put 12 grams on bottom, 1 mole on top. Because the molar mass is 12 grams per mole. I don't need to remember mass divided by molar mass equals moles. I don't need to memorize that equation because I'm simply putting grams on top, grams on bottom, grams cancel out. Units I'm left with is moles. What is my question asking for? Moles. So I know I've set this up right. As long as my units are matching what is asked for, I know I'm probably set this up right. There's not a lot of added tricks like it is in physics, where it's like, if I did velocity, it's like 1/2. So it's like like acceleration is like 1/2 v/t squared or something like that. I can't remember the exact number, but there's no extra halves in there usually, unless you're calculating, say, area of a circle or something like that. There's no extra units in there usually most of the time. But so 31 divided by 12 would give me my answer. So I'm canceling out units all the way across. Now, why did we have to take this trip to memory lane back to chapter 3? Because we are coming back to here. That's where we're going to. We need, the first thing we'll learn is the mole to mole conversion. So right there, I said moles. But to be all accurate, I should have said moles of carbon per grams of carbon. Because now we're going to use the ratio from the balanced chemical equation to convert moles of one compound, we're going to call it generic compound A, to moles of compound B. Is what there, the ratio, and the ratio will literally depend on the numbers in the balanced chemical equation. I can convert, this equation says 2 moles of C6H6, which is benzene, carcinogen, common rocket fuel, solvent, very flammable, has burns in oxygen, 15 moles of oxygen to be exact, to produce 12 moles of CO2 and 6 moles of H2O. I've already balanced it for us. But we can use this to answer any question about this reaction. We could say, if I have so much benzene, how many moles of oxygen would it need? If I have so much benzene, how many moles of CO2 would be generated? If I have this much benzene, how much water could be generated? But I could also ask, if I have this much oxygen, how much benzene would we need? If I have just one value for this equation, I can use this to answer anything about the other 3 values because of the balanced chemical equation. So we're going to set that up. If I have 2.4 moles of benzene, how many moles of oxygen will react with it? Well, I'm going to set up the balanced chemical equation. Say, so 2.4 over 1, and so I'm going to multiply by 15 over 2. Why is it 15 over 2 and not 2 over 15? Well, because we have moles of benzene on top, so we need moles of benzene on bottom. So I'm going to use the coefficient for benzene on bottom. Why is it 15 and not 12 or 6? Well, we're asking a question about oxygen, so I'm going to use the coefficient for oxygen. And so then I just carry the reaction through. I say 2.4 divided by 2 is 1.2. 1.2 times 15 is 18. So, and I follow that through, and now I say, so 18 moles of oxygen would be needed to fully react with 2.4 moles of benzene. How many moles of CO2 would be generated by this? So 2.4 moles. So I'm going to still use that 2 because I'm still dealing with 2.4 moles of benzene. So, but now I've changed my coefficient to 12 to match the question of asking about CO2. So now 2.4, 1.2, then 12 times 1.2 gives us 14. Technically, it's probably more answer, but rounding for sig fig's sake. Please note, while sig figs may come back up in the slides on a test type situation, I will rarely call you on a sig fig. It's, yes, you probably should, but it's not the most important thing in the world. I'm not going to be, if it's, you took this out to one more decimal place, I'm not going to be like, oh, that's 0 points. I'll probably give you points for it anyways. Okay. Now, we're going to always take this one step further, because more often than not, we will not know how many moles we have. Instead, we are going to use the mass to mass conversion. The most common thing we will do is mass to mass, because we can weigh all these things out. We have a balance in the lab. We can weigh compound A and compound B and know the mass of each. If we know the mass of each, we can convert the moles of each. Now, this is something I do just about every day. Every day I'm in the lab and I'm weighing sun out for a reaction, I'm going to have to do this simple math. It's not super hard, but it is something we have to keep in mind. I want to turn grams of A to grams of B. Unfortunately, because each atom weighs different masses, we can't go directly there. Carbon weighs 12 grams per mole. Iron weighs 56 grams per mole. If I said I have 56 grams of iron and 56 grams of carbon, you have a totally different amount of atoms. So we're always going to have to go grams to moles, moles to moles, moles back to grams. To get there, we're always going to use our molar mass to get to moles, our molar mass to get from moles of B back to grams, and in between, we're going to use our balanced chemical equation. And that's the basic premise of what we're doing every time on this, in most of this chapter. Now, we're looking at this example of benzene. Instead of 2.4 moles, I took 78 grams of benzene. I took a beaker, poured a bunch of benzene in it, and lit it on fire, and then said, how much water could I collect? So how would I do that? So I'm going to say I take each carbon is 12 grams per mole. 6 carbons is 72. Each hydrogen is 1 gram per mole, and we have 6 carbons, so 6. So 72 plus 6 is 78 grams per mole. So calculate the moles of benzene. So 78 grams divided by 78 grams per mole gives me 1 mole of benzene. The next step, I'm going to use the balanced chemical equation to figure out how much moles of water would I form. So 1 mole of benzene, we divide by 2. We divide by 2. And moles of benzene, to cancel the benzene, times by 6 moles of water to give us the moles of water. So that's going to give us 3 moles of water. Then finally, the molar mass of water. Oxygen is 16, H is 1, the other H is 1, the molar mass is 18. Moles of water, cancel moles of water to give us 3 times 18, 54 grams of water. And so this is the general premise we'll do on almost each and every problem. We're going to count grams to moles, back into grams. Grams to moles to grams. I know it's a mouthful. I know it's a little tedious, but setting this up, it's the same process each time, just with a different equation. If you understand the process, it will be the same thing. It will be boring, perhaps, but it won't be new, novel, and surprising if you get this down. Which hopefully new and novel, surprising is not what you want to see on a test. So if I have instead 14 grams of benzene and I asked how much oxygen would we need to fully burn it. So once again, 14 grams, we divide by 78 grams per mole. We look at the balanced equation, 2 to 15. I know I need the 2 on bottom, 15 on top, because we need moles of benzene to cancel with moles of benzene. I know that moles of benzene is on top because I needed grams of benzene to cancel grams of benzene. So finally, then we use the molar mass of oxygen. Moles of oxygen, 32 grams of oxygen. You'd say 14 grams of benzene needs 43 grams of oxygen to fully burn. And so first thing you'd always want to do on this question, look at what you're given, look at what you're asked for, and think about how we're going to get there. The thing you always need to know, we're almost always going to go through moles. Almost always going to go through moles. So you got to look at molar masses. You could find the molar mass of every compound in this reaction. but none of these questions have asked you about CO2, so finding the molar mass of CO2 would not be helpful. So we want to diagram where we want to go. Okay, nope, I want to be over here. Now, limiting reactants. This is a new concept, but it's not super new. We've actually seen this a couple times already. We've seen this in lab number 3 when we looked at magnesium burning to get magnesium oxide. We used magnesium in the presence of oxygen because oxygen is in our atmosphere and in large abundance. The amount of magnesium oxide was limited by the amount of magnesium we started with. In lab yesterday, we put magnesium into hydrochloric acid and burned it and tried to dissolve it. You noticed as you added hydrochloric acid, it bubbled, but then eventually it would stop. If you added another drop of hydrochloric acid, it would bubble some more and eventually stop. This is a case where the hydrochloric acid is our limiting reactant. And if you kept on adding hydrochloric acid, you would eventually dissolve all of that magnesium. But that's not the case in this situation. So the idea here for a limiting reactant is oftentimes reactions will not completely react. So some reactants will get left behind. And in fact, in order to maximize the yield, maximize how much product we get, we're going to put one reactant, which is often pretty cheap, in excess. So if I have a thing like, well, I need lead and a bunch of gold, I don't want any gold left behind. I want lead left behind. Lead's pretty cheap. Pretty cheap. So I would put lead in excess, and so all the gold would get used up. So we want the limiting, if the guy in excess doesn't get used up, the other guy gets fully consumed. That is the limiting reagent or reactant. It is the guy that controls how much product will get formed. Now, so we have an example here. We mix magnesium with hydrochloric acid. In these two situations, B and C, in B, we see the bubbles have stopped. There's magnesium strip left. So clearly, if this stopped, well, we must have run out of acid. We can't form any more hydrogen gas if we have no more H+. In this case, the magnesium has fully dissolved. So we can't form any more H2 gas if we have no more magnesium to dissolve. It's all reacted. So in this case, depending on which one you have in excess, says what is going to be limited at the very end. So where we're going to go with this is we're going to use the limiting reactant to find out how much product could be formed. And I know this is going to be a lot of math, but this is not actually any new math. It is going to be, long story short, it is going to be the grams to moles to moles to grams, and you can just do it twice. You double the length of the problem a bit, but it's not really a new thing. It's just twice of an old thing. So we're going to just do this twice. To find a limiting reactant, you're going to follow 2 steps. At least this is what the book suggests. 1, determine the amount of reactant B needed to react with reactant A, and then compare the calculated quantity of B with the actual quantity of B. So if I have 10 grams of A and 10 grams of B, so 10 of both, and I calculate how much B would be needed to react with 10 grams of A. If I calculate it and I say there's 8 grams of B that would need to react with 10 grams of A. So the calculated amount is less than the actual amount. If the calculated amount is less than the actual amount, then the A is limiting. So 10 grams of A would react with 8 grams of B and would run out of A. You'd have 2 grams of B left. Now, hypothetically, do the same math. You get that I need 12 grams of B to react with 10 grams of A. And I have 10 grams of B. I am 2 grams shy of what I would need. So if the actual amount is less than the calculated amount, then B would run out first. B is the limiting. And of course, if the calculated amount and the actual amount are the same, then neither would be limiting and both guys would be consumed fully. But so what is this going to mean? We are going to, where would you see this in a question? You might see which guy would run out first. You might see how much of the excess is left. You might see what is the maximum amount of product that could be formed. But so for this first problem, I say 16 molecules of methanol, 25 molecules of oxygen. I'm keeping this as on the molecule side so we don't have to do grams to moles. So just looking at this, which guy will run out first, methanol or oxygen? Well, I could convert oxygen to methanol, or I could convert methanol to oxygen like I do down here to find out which one is limiting. In this case, 16 divided by 2 times 3. So divided by, you got 8. 8 times 3 is 24. 24 oxygens would be used up. I have 25 oxygens. So methanol would be fully consumed before all the oxygen goes away. Would have 1 molecule of oxygen left. So methanol is limiting. If I did it from, If I did it from oxygen's standpoint, you will get the same results, but a different way. If I said, how much oxygen? I have 25 molecules of oxygen. This is O2. And there's 3 molecules, 3 moles O2 per 2 moles CH4O. So 50 divided by 3. Let's see, 1. You would get 16.67 molecules of methanol. So CH4O. So what does that mean? From oxygen standpoint, you need 16.67 or 16 2/3 of a molecule to fully consume 25 molecules. We have 16 molecules. 16 is less than 16 2/3. So once again, methanol runs out first. So it doesn't matter which way we look at this, methanol remains limiting. Now, where we're going to eventually go is to here, where we're going to have to do it from grams and grams. We're going to look at this moles of reactants to grams and grams of reactants. Once we know the limiting reagent, we can figure out how much of a product is formed. So this example right here, the 4 iron plus 3 oxygen goes to 2 iron oxide. Is often going to be the example of the question, what is the limiting reactant and how much iron oxide could be formed? If I have a Chevy, like an old Chevy truck with the steel frame, it's been around the block a couple times, and it starts to rust. Which one out first? Am I going to kick my frame and the frame's going to fall off because it's all rust? All the iron, the steel in the frame rusted up? or is there still some good steel underneath that pile of rust? So we're going to ask it, how many moles of iron oxide could be formed? So what's the dead giveaway that you have a limiting reagent problem? You have an amount of 2 different reactants. Whenever you see a quantity for 2 different reactants, that is a dead giveaway. You're dealing with a limiting reagent style problem, because otherwise we'll just say, oh, I have 16.7 moles of iron, and I wouldn't bother to tell you the amount of oxygen, and you'll just convert it from iron. But because I give you both, we have to figure out which one gets used up first. So I'm going to convert, in this case, moles. I'm going to keep it easy for this problem. Moles. 16.7. We use the balanced chemical reaction. Divide by 4, multiply by 3. You would see that I need 12.53 moles of oxygen to fully consume the iron. So that means 12.53 versus 12.2. Oxygen is limiting. With that in mind, calculating how much iron oxide I could form, 12.2 divided by 3 times 2 gives us, you'd form 8.13 moles of rust. Now I'm going to actually kind of work this one out. But copper plus oxide, if we have 85 grams of copper and 27 grams of oxygen, which is a limiting reactant, and how much copper oxide could be formed. Now you may want to say, ooh, copper's in a greater quantity. There's a much bigger mass of copper. So clearly oxygen should be limiting. But remember, each atom has a different mass, and we have to compare the actual masses. We can't just look at that quantity big, that quantity small, ooga me smash, rock. So copper has a molar mass of 63.5, almost 64. And you need 2 moles of copper per every 1 mole of oxygen. Finally, 32 grams of oxygen. You'd see that, do this math, grams cancel grams, moles cancel moles, O2 moles cancel moles, we're left with grams of oxygen. You would need 21 grams of oxygen to use up copper. So that's going to mean copper runs out first, because 21 is smaller than 27. Then we'll just do this one more time. 85 divided by 63.55. 2 per 2 times 79.55. Give us 110 grams of copper oxide as the product. We're going to do one more slide, and that's where we're going to stop. This will be the exact same spot as the Tuesday, Thursday class. This is our actual practice problem. Actual practice problem. So let's look at this. Let me write this down first. We have a balanced chemical reaction. This is a smelting furnace. Son, you take some iron, you want to make some steel, you dig some iron out of the mountain, you take some iron oxide, some hematite, you throw it into a blast furnace with a bunch of charcoal, you add some oxygen, and you're going to get some pure steel and some CO2 byproduct. And now we're going to assume oxygen is just going to be present. We're going to pump it in. It's not going to be the limiting reagent. So, but if I have 480 grams of iron oxide and 144 grams of carbon, how much iron could I produce? How much iron could I produce? So it doesn't really matter which one you convert. You can do it either one. But first things first, I'm going to look up the 3 major molar masses. Iron is 56. Technically, it's 55.85. We're going to say 56 for this. Carbon, it's 12. Iron oxide, 56 times 2 is what? 112. 16 times 3 is 48. 112 times 48 is, well, plus 148 is 160. You think, wow, he did that fast. It's because I've done this question so many times. I know iron. I know this. I've done this. It's muscle memory. But okay. Which one of these guys runs out first? Now, you may want to say, well, clearly, carbon weighs a lot less. But got to remember, iron oxide weighs a lot more. So which one will run out first? I think in the equation I do iron, I check iron, but I'm going to mix it up. We'll check carbon. 144 grams of carbon. There's 12 grams of carbon for 1 mole of carbon. The reason I do it like this, grams cancels grams. I'm always going to show my work so you can see where I'm getting these numbers, where I'm pulling them from. I'm always going to try to show the complete unit unless I get really, really lazy, because without the complete unit, it's just like words on a board. This is trying to give context. Balanced chemical equation, 6 to 2. 6 moles carbon for every 2 moles iron oxide. Then finally, for every 1 mole of iron oxide, I would have 160 grams iron oxide. In order to compare these guys together, I have to compare grams to grams. I cannot compare grams to moles. I can't compare grams of carbon to grams of iron. I have to compare equal units. You can't compare apples to oranges. I have to compare grams of iron oxide to grams of iron oxide. So doing the math. So 144 divided by 12 is 12. 12 times 2 divided by 6 is 4. 4 times 160 is 640. So 144 grams of carbon could react with 640 grams of iron oxide. So which one is less, 640 or 480? Well, we hopefully say 480. So what does that mean? The iron oxide runs out first, which is probably a good thing. Iron oxide is a lot more expensive to get than, say, coal, where we happen to have a lot of coal in this country for our benefit. So we're going to take 480 grams of iron oxide. I'm going to turn this into moles of iron oxide. 160 grams, Fe2O3, 1 mole. Look at the balanced equation. For every 2 moles of iron oxide, we have 4 moles of iron. 2O3, 4 moles iron. And then for every 1 mole of iron, it weighs 56 grams. So whatever you do, make sure you got order of operations down in your calculator, or do it step by step by step. I don't care how you got to do this. Make sure you don't screw this up, because it's no bigger crime here is to set this up perfectly on paper and then come out with a number that makes no sense. I've seen it done. Seen it done in the lab many times. So we got 40 divided by 160, it's 3. Times 4 over 2 is 6. Times 56 is, we would make 336 grams of iron. 336 grams of iron is our product. And that is this whole process. Now, we're going to stop there. We're out of time. But where we're going to head with this is to limiting reagents. That this is not always going to be a perfect process. We may be able to produce 336 grams of iron, but that's in a perfect world. Maybe we have some careless steel workers. They spill some on the floor. Maybe there's impurities in that iron oxide, and so we cannot get 336 grams. And we'll be able to calculate this like we should have been able to do during the MGO lab again. But that is where we're stopping. Thank you for your time. Have a good day.